Fine. Okay, nice. So, hi. Welcome to my talk. Together we will today explore what the PyTorch JIT can do and what it cannot do. First of all, something about me. I'm Tilman. I'm working as a deep learning engineer at IAV Digital Lab, where we are doing the future of engineering. And I'm also a PhD student at TU Berlin under Professor Clemens Gümann, where I'm doing research about, where I'm doing research about predictive maintenance and transfer learning. Now that we've got that out of the way, what are we even talking about today, or what am I talking about? We want to learn about the JIT, which is short for just-in-time compiler. A just-in-time compiler is just a compiler that runs during the execution time of your program and just-in-time compiles the source code or the bytecode into machine code. In our special case, it means that the JIT will compile the forward function of our neural network model, which is written in Python in the PyTorch framework, into a computation graph as we should know it from frameworks like TensorFlow or so on. This computation graph can then be directly executed in the C++ runtime of PyTorch, which means no more callbacks back to Python. This has several pros, especially for one use case, which is deployment. You can use it for development too, but here maybe the dynamic structure of the Python-defined computation in PyTorch is more, it's better for you while developing, but in deployment you want maybe your static graph for easy export and for optimization. Yeah, in the title of the talk, I made some promises. Just a quick reminder. The proposal for the talk was some time ago, and these promises are based on my current my understanding that I had of the time about the JIT, and also on a different PyTorch version than we have today. So when I started working on this, we still had 1.01 or something, and now we have 1.2. So some things changed, but today we will explore if or how these promises are fulfilled by the PyTorch JIT. First promise is minimize dependencies. So you don't want to put all your development code on your deployment system. You want to move minimum of code and minimum of data from one system to the other. We will see how that works. Then probably you don't want your plain code on your deployment system for nosy people like your customers. And you want your network to be as fast as possible in deployment. That means we want to boost performance. Performance here, really execution speed, not accuracy or something like that. So first of all, we're going to do some imports here. This is a live Jupyter notebook, so everything I do here will be live and maybe breaks. I hope not. But first of all, we're doing the imports. So we're getting PyTorch, the Torch Vision library, which just contains some pre-trained vision models that we're going to use. And we're importing the JIT module itself, and then just some stuff that I'm going to need for this presentation. The network we are working with will be AlexNet, which will be pre-trained. The reason for AlexNet is it's simple, and my laptop is not that powerful. And if we want to stay in the 30 minutes, we have to take something simple. So first we're going to execute our imports, and then we're having a look at our network structure. As we can see here, AlexNet, really simple. We have a feature extractor of convolution layers. We have an average pool, and then we have a classifier which consists of fully connected layers. And as we can see, all the information that we need about the network, like which kind of convolutions, which kernel size, which stride, everything is in there. So everything we need to know about the network structure, we can learn from this print, basically. Next, we want to build our control group. So now we have our AlexNet, and we want to move it to a deployment system. How can we do that? There are basically two conventional ways to save a model in PyTorch, and a more exotic way. The first one would be just pickling the whole object. which is not the recommended way, by the way. So we're using the torch.save command, which uses pickle under the hood and just saves the whole object, a Python object, to a file. Works. The second way, which is the recommended way for doing it without the JIT, is just saving the weights of your network. So the weights and all the buffers of the PyTorch network are saved in the state dict of the network. And we can just take the state dict, which is just a Python dictionary, and then save it to a pickle file. The difference is that we now would need to reinstantiate the object ourselves and load the state dict back into the object. We can do that too. The more exotic way would be exporting an ONNX graph. So ONNX stands for Open Neural Network Exchange Format, which is really nice because if we export it like that, we can import it in other frameworks like Caffe2 or I think MXNet or something like that. So to do that, we need to build the network graph with an exemplary input, set our network to eval, because we can change that later, and then just export it with the ONNX export function and get an ONNX file. That takes a little bit longer because it has to build the graph first, but now we have 3 different files on our disk where we saved our network. Okay, this is our control group. Now we're going to move on to how to use the JIT itself. It's pretty simple and looks a little bit like the ONNX stuff. So first we define an exemplary input for our network, which would be this random noise image there. We set our network to eval again, and then we're going to trace the model. So there are 2 ways to using the JIT. One is tracing, the other is scripting. Tracing is the easier one, and I'm going to stay in with tracing here just because scripting would be a whole talk on itself, and this is an introductory talk, so we're going to trace for now. Tracing just means we pipe the exemplary input through our network, and each operation is recorded and then put into the computation graph. This graph is then saved to a script module or a trace module, which we can have a look at then. So this is the computation graph, and I think nobody can read it. So it's not really that human readable anymore, but it does exactly the same as the forward function of the LXNet does. Now that we have our computation graph, we can save it to disk, which we do with the jit.save command, which works just like the torch.save command, but for traced and scripted models, which works too. And we're good to go. Basically, that's it. So this is how you use the JIT for saving your model. Now we're gonna head over to our deployment system and see if how it all works out. So to do that, we are just going to use another Jupyter notebook, which is not only separate from the Jupyter notebook, but also runs in a separate virtual environment so that we really have a clean cut between our development and our deployment system. So for the deployment environment, again, we are going to import some stuff. So we're going to import Torch, the JIT, NumPy, and all the stuff we need for deployment. And as you can see here, we're not importing Torch Vision. The reason is that Torch Vision is not even installed in this environment. So Torch Vision would be the contains the code for our network, and we maybe don't want to have the code for our network on our deployment system. So it's not there, and we will see how it works out for all the ways we saved our models. So this is our deployment code, which is just a small function that takes an image from disk, pipes it through the network, and says which class the network predicted. And now we're going to see how if our first promise is fulfilled. We will see how the JIT minimized the dependencies of our network. So first, we're going for our control group. We're trying to load the whole pickled Python object, and we will fail because pickle in the background tries to automatically reinstantiate the Python object that we saved, and it can only do that if it has the Python code for that. And as Torch Vision is not installed, it can't find the Python code, and it can't reinstantiate the object. This is also why this is not the recommended way to save a model, because if you're doing some refactoring or you change something on your Python code of your model and try to load an old version, it won't work anymore because the Python code is different or the Python code is not even there. So best practice is saving only the weights, because then you can, in the event of refactoring happening, can stitch it together yourself. So this doesn't work. Next thing would be loading the stake, which would be the recommended thing to do, which we can do just fine. But as I said, we still need the Python code to get the architecture of our network, and we don't have that. So while we now have the weights, we don't have the architecture, and we can't do any inference with that. Doesn't work too. So the last one, the exotic one, would be Onyx, and I'm not shitting you, PyTorch has no import function for Onyx. You can only export it. So I don't know what they thought, but even the tutorial says, okay, now we're exporting it from PyTorch and we're loading it in Caffe 2, and Caffe 2 was merged into PyTorch, and Caffe 2 has an import function, but PyTorch not. I don't know what happened there, but it was not good. So can't use that either. Now the JIT to the rescue. We're going to try to load our traced model with the JIT.load function, which works, obviously. The load function here works just as the torch.load function would, with the difference that if you would have saved with torch.save from the GPU, torch load would try to put it on the GPU again, and JIT.load always puts it on the CPU first, and you have to move it then. That's the only difference basically, but JIT.load works on traced models. So now that we have our model, we can use it in deployment. We are going to take this little JPEG there and just try if our pre-trained model works as intended, which it does, because it knows that is a picture of a cat, which means we successfully cut out all of the development code that we have as a dependency, which is just what we wanted to do. But the JIT doesn't stop there. Maybe you not only want to cut out your PyTorch code, Python code, but also Python itself. So what if you want to deploy in C++? That's pretty easy actually, because PyTorch has now, with I think 1.0, a C++ interface, and we can just load the traced model into C++, which is pretty simple. I just hope nobody here is a C++ expert, because I'm not, and I can say some weird stuff now. What we're doing is we're importing the script header, which has all of the stuff that we need for loading and using a script, a traced module. First, we're going to, instantiate the script module over there. Do I have I have a mouse. Here we instantiate the script module, and then we are just using the same load function that we would have used in Python to load the model with the path that we get from our first command line argument. If it throws an error, something went wrong, otherwise we get an OK. And that's it. That's how you load the model. It's pretty simple, because the PyTorch team tried for the C++ interface to be as similar to the Python interface as possible. Using it is basically the same. So first you have to build your input vector. So you're using a standard vector from C++ of I values, which is a little bit different, but you casting is done automatically. So you take a random tensor, push it into your vector, and then you're defining an output tensor, and then you just call the forward function on your input vector, get an I value back, convert it to a tensor, and got your output. This is pretty simple, and you not only have to take you don't have to take my word for it. I implemented it myself with a lot of help of the documentation. So we're going to take our traced model, put it into the example app, get an OK, and then it will run 10 times, and then output a profiling file that we can later inspect to see what our network has done. So now we even cut out the Python dependency itself. So I'd say the promise of minimizing dependencies gets a check mark. Moving on, with the success under the hood, we want to see if we can hide our code with the JIT. So as I said, we cut out the Python code itself. So there's no plain text code floating around of our network in our deployment system. But can we somehow still see what the network is about? So we're just trying to print now our traced network, and we can see that the overall architecture with the feature extractor and the classifier and the average pool is still there. But the modules itself don't have this detailed information anymore that it had before. But maybe we can go a little bit further, and we'll see what kind of information we can get out of our network. So we are going to have a look at all of the functions that our network module has. And it's a lot, and there are some duplicates, but the most interesting one would be this here, which is called code. This is a property function, and we're just gonna see what it contains, and it's just the Python code of our model. It looks a little bit contrived because it's not Python code, it's Torch script, which is a subset of Python that the JIT understands, so some convenience functions are missing, but in the end, as you can see, you have the convolution here. It gets the weight. You know, it has this kernel size and which stride, and if it has a bias and so on. So in the end, we get the architecture of that stuff. So we get the architecture. Can we access the weights too? We're just going to have a look at what kind of member variables our first module has of the feature extractor. And there we have the parameter dictionary, which normally contains all of the weights. So let's have a look at the keys there. And the only keys are called weight and bias. So we're going to have a look at the shape. And yes, it's a tensor. It has the right shape for our first convolution. So in the end, yes, the code is better hidden than having plain Python code on your deployment system, but everybody with a Python interpreter can basically access it. So it gets a meh. Okay, not so nice, but still we have one last promise to explore. We're gonna head back to the system we trained on, because now we want to compare the traced network in terms of speed against the untraced network. Yeah, boost performance. Does it really boost execution time? For that, we're going to run our forward pass 10 times by 10 times, just to see if how the distribution of runtimes is. And we can see here we got 686 milliseconds with 61 milliseconds of standard deviation here for 10 runs. This is for the untraced network, the first one. The second one is for the traced network. A little bit of info about how I did this. Normally, if you're doing timing in Jupyter notebooks, you're using the magic timeit command. That does not really work reliably here because PyTorch in itself works asynchronously, because the computation, especially the GPU computations, are just put into a queue and then executed, so the Python code can return before the execution of the calculation is even finished. And this is why we need to use the built-in profiler of Torch, which really gives us the time spent in the C++ runtime. And as we can see, the traced network is a little bit faster. It's not that much, but it's a little. And just to be on the statistically safe side, we're going to use ANOVA to see if it's statistically significant difference between the runs, and it's not. So as we can see here, the standard deviation is still in the range when we can use ANOVA. And in the end, it's not really a statistically significant difference here. But this is only For CPU, let's head on to GPU runtime. And as you can maybe see, this laptop probably doesn't have a dedicated CUDA-capable GPU. So I did this beforehand on a machine with a 1080 Ti. And we're going to load the results and have the same look here. And as we can see here, the network that was traced is really faster, and the difference is even significant. We have to take this with a grain of salt, because the standard deviation of the traced one is much smaller than the standard deviation of the untraced one, but still we're getting 2 milliseconds, but 2 milliseconds for 10 images. So in the end, when just doing one image, we get 0.2 milliseconds of performance increase, which is maybe statistically significant, but practically not really. Which is really sad, because this is another promise that seems not to be fulfilled. But AlexNet is just one network. Maybe it's just too simple. There's nothing to optimize. This is why I ran the same thing for all the networks in Torch Vision. And as you can see, it doesn't get really better, because most of the time, both types, like the traced and the untraced ones, are both fast. But sometimes the one is a little bit ahead and sometimes the other is a little bit ahead. It's even statistically significant because the standard deviation is so low, but in practical terms, you can't even see the difference on this beamer here. The only network where it really worked and the traced one was faster was the Google Net, also known as Inception V1, where the traced one is really faster. And I thought, okay, why is that? And I looked at the code and I can't really say. So the code was written by the same people that wrote all the other networks, and there's nothing that is really different on this network, and especially because when Inception V3 is not really that much faster, and it's practically the same base of an architecture. So this is a huge problem with the JIT, that even though the PyTorch team says that the execution is optimized, we don't really know what is optimized, because here it seems that there's just nothing to optimize in this simple feed-forward networks. So in the end, boost performance gets a meh too, because statistically yes, practical no, but maybe, I don't know why. So if any one of you has some insight in that, I'd like to really to know. So in the end, our promises again, minimize dependencies gets a definitely yes, and all the both others get a meh, because a bit, but not really. So as a conclusion here, I'd say I will still use that, because it's in what it's supposed to do, namely minimizing dependencies for your deployment. It's really good, and the other ones are at least an improvement on the status quo, but not a really good improvement. But we will see what others and what the next releases bring. So I promised in my abstract that I give some hands-on advice, but I don't have that much time, so I'm just going to be really quick. First advice that I'd give is avoid non-traceable code. Tracing is really the most simple thing you can do with a JIT. Scripting gets really, really hard, because you have to write Torch script, which is Python, but is lacking some stuff, and you don't always know what is lacking, and the error messages are really not that helpful. So if you can trace your code, which you can always do if you don't have any input dependent control flows, something like ifs that are dependent on the shape, or RNN stuff that needs a dynamic loop, number of loops, then you can just trace it. And most networks are feed forward anyway. So yeah. Then second thing, if you need to script, convert your model module by module. You can mix scripting and tracing. So try to find out which of your modules is the problem, and then only script that. If you then trace the whole module, the script module will be still there and work as expected, so you don't have to script your whole network, but only the one module where it fails, basically. And the last one is include the interface code into your graph. That just means when you're using a deployment system, you probably want a general interface for how it works. You want to give it an image from your disk as a NumPy array maybe, and then you're expecting it to output the index of the most probable class. Just include stuff like input normalization, softmax, and all the other stuff into your graph that makes your code much cleaner on the deployment side and much easier to swap out networks as you go. Yeah, that's it from my side. This talk is on GitHub, so you can play around with it yourself. This C++ example is also there. I put the link on the description of the talk, but I didn't find it myself. So anyway, make a photo or something. Yeah, that's it. I'm open for questions.
Thanks a lot for this thorough introduction. Are there any questions? If not, I myself have one. So, like my favorite thing about PyTorch is actually that I do have like the full Python control flow at my hands. So how well does the JIT compiler actually deal with that?
As I tried to say, tracing just throws away all the control flow. It just records the one computation flow that you have. If you want to retain your control, then you have to script it, which you can most of the time, but then you have to see, are you using member variables of your module? Then it's a little bit different in Torch script than it is in Python itself, and there it gets complicated. Yes, you can, but it will need some refactoring. There was another question over there, I think.
Great.
Do you have any experience with Torch script and performance? How that affects performance?
If you mean if Torch script is basically slower than just tracing it, you mean?
For example?
Not directly, just from intuition. The thing is, most of the modules that there are in the .nn module are written in Torch script. So it shouldn't make any difference because you just stay in the C++ runtime and yeah, you don't go ever back to Python, so it shouldn't make a difference, but I didn't test it myself.
Any more questions? If that's not the case, then let's thank Tilman again for his nice talk.